On a frozen morning in February 1943, John Niedermair stood on the beach at Quonset Point, Rhode Island, watching the commanding officer of LST-1 hesitate at the helm of a ship worth $2 million. The young lieutenant had just received an order that violated every instinct drilled into him at the Naval Academy, an order that contradicted centuries of maritime tradition encoded in the Articles for the Government of the United States Navy, which clearly stated that any officer who deliberately ran his ship aground would face court-martial. Niedermair, a civilian naval architect from the Bureau of Ships, had just told him to aim the bow directly at the beach and floor the throttle. Drive the flat-bottomed vessel onto the sand at full speed, 10 knots. Ram it deliberately into the shallows until the keel scraped bottom and the bow doors opened onto dry land. The lieutenant looked at Niedermair like he'd lost his mind. Behind them, a gallery of Navy brass watched through binoculars from the shore. Admirals who'd spent their careers commanding deep-draft warships that avoided coastlines like poison. Engineers who'd calculated load stresses and hull tolerances. Procurement officers who'd already signed contracts for over 200 of these strange vessels based on Niedermair's sketches. If this test failed, if the LST buckled or cracked or rolled when it hit the beach, the entire amphibious invasion strategy for World War II would collapse before it began. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The ship that sat offshore that morning looked like nothing the Navy had ever commissioned. 328 feet of welded steel with a flat bottom, a blunt bow, and a profile so ungainly that sailors would soon nickname it Large Slow Target. But LST-1 represented something more profound than ugly engineering. It embodied a gamble that challenged fundamental assumptions about what ships could do and who could build them. 15 months earlier, in November 1941, the concept didn't exist. The United States wasn't even at war yet. But British Prime Minister Winston Churchill had already identified the critical weakness in Allied strategy. Every amphibious invasion since Gallipoli in World War I had failed for the same reason. Troops and tanks had to be offloaded at established ports or transferred from ships to small landing craft in open water, then ferried to beaches in vulnerable shuttles. Defenders simply concentrated fire on the ports and the transfer points. The logistics became killing zones. Churchill wanted something impossible. A ship large enough to cross an ocean carrying tanks and heavy equipment, but shallow enough to drive directly onto a beach without docks or piers. A vessel that could unload an entire armoured battalion in minutes rather than hours. Something that didn't exist in any Navy's inventory, and that conventional shipbuilding wisdom said couldn't be built. At the Atlantic Conference in August 1941, Churchill and President Franklin Roosevelt agreed that Britain desperately needed these vessels. The Royal Navy's initial attempts had produced the Boxer class, 3 ships that could carry 13 Churchill tanks across the Channel, but they drew too much water to actually beach. They required enormous extending ramps that took too long to deploy and broke under stress. The British needed better. They needed Americans to design it. In November 1941, a small British delegation arrived in Washington and met with the Navy's Bureau of Ships. They presented the requirements. The ship had to carry at least 40 tanks or a comparable weight in trucks, artillery, and supplies. It needed to cross the Atlantic under its own power through winter storms. Once it reached the invasion coast, it had to drive onto any beach, with a gentle slope, open doors in the bow, drop a ramp, and disgorge its cargo directly onto sand. Then, somehow, it had to pull itself backward off that beach and return to sea for another load. The Bureau of Ships gave the project to Niedermair, their technical director of preliminary ship design. He was 42 years old, a graduate of Webb Institute with 20 years of experience designing everything from tugboats to battleships. He understood immediately that he couldn't split the difference. Trying to design a ship that was somewhat deep and somewhat shallow would create something that failed at both tasks. He needed a ship that could transform itself. Deep when crossing oceans, shallow when assaulting beaches. Within 5 days, Niedermair had sketched a solution so simple it seemed obvious in retrospect, though no one had thought of it before. ballast tanks, massive water tanks built into the bow and stern. At sea, the ship would pump seawater into those tanks, adding hundreds of tons of weight that pushed the hull deeper into the water. The added draft provided stability in rough weather. The ship would ride low and heavy, ploughing through Atlantic storms without capsizing. When approaching a landing beach, the crew would engage powerful pumps and blow the ballast tanks dry. The ship would rise in the water as it shed that weight, reducing its draft from 14 feet to less than 4 feet at the bow. With that shallow draft, it could drive right up onto a sloping beach until the bow grounded and the doors could open. Niedermair sent his rough sketch to the British Admiralty on November 5, 1941. They approved it immediately. Within weeks, Britain had formally requested that America build 200 of these landing ships, tank, under the Lend-Lease program. But Niedermair's sketch was just a concept. Turning it into a working vessel that could survive both ocean crossings and beach assaults required solving 100 engineering problems that no one had encountered before. The Bureau of Ships initially designed the LST at 280 feet long. That length lasted through January 1942 before someone realized it wouldn't carry enough cargo to justify its construction cost. They stretched it to 290 feet, then to 328 feet in the final design. Each extension required recalculating the hull stresses, the ballast volumes, the engine power, the structural reinforcement. The bow had to be strong enough to smash onto beaches repeatedly without crumpling, but it also had to incorporate massive clamshell doors that could open outward and a ramp that could drop onto sand at varying slopes. The doors became 14 feet wide, big enough for any Allied tank to pass through. Behind the doors, the tank deck stretched the full length of the ship, a cavernous space that could hold 20 Sherman tanks or an equivalent weight of trucks, artillery pieces, ammunition, and supplies. The engines posed their own challenge. The Navy wanted diesel power for fuel efficiency and fire safety, but the preferred engines weren't available in the quantities needed. Instead, the LST got heavy steam reciprocating engines salvaged from cancelled frigate programs. These monsters weighed far more than expected and required complete redesign of the engine room spaces. They delivered 2.5 times the power of the unavailable diesels, but at the cost of speed. The final design could manage 11.5 knots maximum, barely faster than a loaded cargo ship. The stern received special attention. Since the LST would drive itself onto beaches bow first, it needed a way to pull itself backward into deep water after unloading. Niedermair's team designed a massive stern anchor, a 5,000-pound hook attached to 900 feet of 1 5/8-inch steel cable. As the ship approached a beach, the crew would drop this anchor offshore in deep water. The cable would pay out as the ship continued forward and grounded itself on the sand. After unloading, a powerful winch would engage and reel in that cable, dragging the entire ship backward off the beach. The system required precise coordination. Drop the anchor too early and the cable would run out before the ship reached the beach. Drop it too late and there wouldn't be enough cable angle to generate the pulling force needed to overcome the suction of wet sand gripping the flat bottom. By January 1942, Niedermair's team had a scale model undergoing tests at the David Taylor Model Basin in Washington. But models in controlled test tanks couldn't answer the real question. Would this thing actually survive the North Atlantic in winter? Would it beach itself without cracking in half? Would the stern anchor system work under combat conditions when everything was chaos and enemy shells were falling? The Navy couldn't wait for a prototype to be built and tested before starting production. The need was too urgent. Pearl Harbor had been attacked in December 1941. America was at war. The invasion of North Africa was being planned for late 1942. Sicily and Italy would follow in 1943. And eventually, the invasion of France that would require more amphibious vessels than had ever been assembled in human history. In February 1942, before a single LST had been completed, Congress authorized construction of hundreds of them. Contracts went out based on Niedermair's blueprints. Shipyards that had never built military vessels received orders for dozens of LSTs. The gamble wasn't just whether the design would work. It was where these ships could be built fast enough to meet the desperate demand. Coastal shipyards were already overwhelmed, building destroyers, cruisers, battleships, and aircraft carriers. Deep water construction facilities couldn't be spared for LSTs. But the LST's flat bottom and shallow draft meant it could be built anywhere with access to a river deep enough to float the hull after launch. That realization led to one of the strangest decisions in naval history. The Navy would build LSTs in cornfields, not literally in agricultural fields, but in industrial facilities located hundreds of miles from the ocean, along the inland waterways of the American heartland. The Bureau of Ships identified 5 locations: Dravo Corporation's facility at Naval Island, Pennsylvania, on the Ohio River near Pittsburgh; American Bridge Company at Ambridge, Pennsylvania, also on the Ohio; Missouri Valley Bridge and Iron Company in Evansville, Indiana; Chicago Bridge and Iron in Seneca, Illinois; and the Jeffboat Yard in Jeffersonville, Indiana. These weren't traditional shipyards. They were bridge builders, steel fabricators, and barge manufacturers. Most of their workers had never seen an ocean. Many had never seen a ship larger than a river towboat. But they had something coastal yards didn't have: expertise in welding massive steel structures and the flexibility to convert their facilities quickly. Dravo Corporation received the lead yard designation. The Navy assigned them to develop the fabrication techniques that all the other inland yards would follow. In January 1942, Navy brass approached Dravo's chairman and president with preliminary blueprints and a contract for dozens of LSTs. They had 9 months to convert part of their Naval Island facility, train thousands of workers, solve the unprecedented engineering challenges, and deliver the first ship. The company had been building river barges and industrial equipment for decades. Ocean-going warships were entirely outside their experience, but they understood steel fabrication and welding on a massive scale. Within days of signing the contract, Dravo began clearing a 66-acre riverside field adjacent to their existing facility to create a new east yard specifically for LST construction. The challenge was staggering. An LST required 3,000 tons of welded steel plates, frames, bulkheads, and fittings, assembled into a watertight hull that could withstand both storm waves and the shock of beaching. Traditional shipbuilding used rivets for major structural connections. Riveted construction was slow but proven. Each rivet had to be individually heated, positioned, and hammered into place by teams of skilled riveters. Welding was faster but riskier. A bad weld could crack under stress, potentially catastrophically. The Liberty ship program was already discovering this, with vessels breaking in half due to welding defects and brittle fracture. But LSTs couldn't be riveted. There wasn't time, and there weren't enough riveters to build hundreds of ships at the speed required. Welding was the only option. Dravo's engineers developed a prefabrication system that broke the ship into manageable sections. 5 area steel plants would manufacture specific hull components, deck sections, bulkheads, and frames according to precise specifications. Those prefabricated elements would arrive at Naval Island, where assembly teams would weld them together in a choreographed sequence. The assembly line approach was revolutionary for shipbuilding. Instead of building one ship at a time from keel to completion, Dravo would have multiple LSTs in various stages of construction simultaneously. One ship would be having its hull sections welded together. Another would be getting its engines installed. A third would be having its electrical systems fitted. A fourth would be undergoing final testing before launch. But there was a problem that no amount of engineering could solve through paperwork. The people who would build these ships had never built ships before. Dravo's peacetime workforce of 2,300 had to expand to over 16,000. Most of those additional workers were recruited from the local population around Pittsburgh. Steel mill workers, factory hands, and increasingly women. When the men went to war, women flooded into the shipyards. By 1943, entire welding crews at Dravo were women. They learned to run welding torches, operate cranes, read blueprints, and assemble sections of hull that weighed several tons each. The training programs ran for weeks, crash courses in skills that traditionally took years to develop. These workers understood steel. They understood heat and metallurgy and structural strength. What they didn't understand was how ships moved through water, how waves stressed hulls, how salt water corroded fittings, how buoyancy and stability worked. They were building ocean-going vessels while having no experiential knowledge of oceans. The first LST keel was laid at Naval Island on June 10, 1942. The construction proceeded in stages that would have seemed chaotic to traditional shipbuilders. Prefabricated bow sections arrived by truck and were lifted into position by massive gantry cranes. Hull plates came pre-cut and pre-formed. Welders worked from detailed sequence cards that specified exactly which welds to complete in what order to minimize residual stresses. The work continued around the clock. 3 shifts, 7 days a week. The urgency was palpable. Every day delayed was another day the Allies couldn't attempt the invasions needed to win the war. By late August 1942, LST-1 was taking recognizable shape. The flat-bottom hull sat in the building way, bow doors installed, tank deck complete, superstructure rising amidships. On September 7, 1942, Labor Day, LST-1 was ready for launch. The event drew enormous crowds. Thousands of people lined the banks of the Ohio River near Emsworth, Pennsylvania. They climbed trees and gathered on rooftops to watch. The ship sat on a greased launching way, held in place by massive timbers. At the signal, workers knocked out the restraining blocks. LST-1 began sliding sideways toward the water. It picked up speed down the launching ramp and hit the Ohio River with a tremendous splash. The impact sent waves rolling across the river, water surging up the banks and soaking spectators who'd stood too close. The crowd erupted in cheers and whistles. This was the largest warship ever launched on America's inland waterways, a combat vessel built hundreds of miles from any ocean by workers who'd never seen naval service. But launching wasn't the same as completion. LST-1 still needed her engines installed, her electrical systems fitted, her weapons mounted, her crew trained. The ship was towed downstream toward the Mississippi River, beginning a journey that would take her through a network of rivers and waterways to the Gulf of Mexico, and from there to her final fitting-out location. The trip itself demonstrated one of the unexpected challenges of the Cornfield Navy. The LST was too tall to fit under many bridges that crossed the rivers. The Navy established a ferry command specifically to transport newly constructed LSTs from inland yards to the coast. This command worked with state and local governments to temporarily modify bridge spans, sometimes raising them, sometimes removing central sections that could be replaced after the ship passed. While LST-1 made her river journey, Dravo continued refining the construction process. The second ship took less time, the third went even faster. By the end of 1942, 23 LSTs were in commission. The other inland yards came online through 1943, each implementing the prefabrication and welding techniques Dravo had pioneered. But ships in commission weren't the same as ships proven in combat. The Navy needed to know whether Niedermair's ballast system would actually work, whether the stern anchor could pull the ship off beaches, whether the hull could withstand both Atlantic storms and the violent impact of deliberate grounding. That's why, in February 1943, they brought LST-1 to Quonset Point, Rhode Island. That's why Niedermair stood on that frozen beach, telling a naval officer to deliberately do what every sailor was trained never to do: run the ship aground at full speed. The test would either vindicate months of design work and millions of dollars of construction, or it would expose the entire amphibious invasion strategy as built on a flawed concept. He turned the bow toward the beach and advanced the throttles. The LST surged forward, accelerating to 10 knots. 11.5 was maximum, but 10 was fast enough to demonstrate the concept. Niedermair watched the bow wave building. The ungainly vessel picked up speed, charging directly toward the sand. Officers on shore held their breath. This was either going to work or it was going to be the most expensive and public failure in the Navy's recent history. The bow hit the shallows. For a moment it looked like the LST might slow, might settle, might stop short of the beach. Then the momentum carried through. The flat bottom rode up the sloping sand. The bow drove forward, water churning alongside, until the entire forward section of the ship grounded solidly on the beach. The bow doors swung open. The ramp dropped onto dry sand. The test worked. LST-1 sat firmly on the beach, bow doors open, ramp extended onto sand that would have been unreachable by any conventional ship. Niedermair allowed himself a moment of satisfaction before the real test began. Getting onto the beach was only half the problem. The LST had to get back off. For several seconds, nothing happened. The suction of wet sand gripped the flat bottom. The LST seemed permanently embedded. Then, almost imperceptibly, the stern began to move. Inch by inch, the ship slid backward. The bow lifted slightly as the hull broke free from the sand's grip. The winch continued pulling. Water flooded back under the hull. Within minutes, LST-1 was floating free in deeper water, ready to turn around and make another approach. Niedermair had been right. The ballast system worked. The stern anchor system worked. The reinforced bow could take the impact. The fundamental concept was sound. The admirals watching from shore sent immediate reports to Washington. LST production could proceed at full scale. The invasion plans could move forward. But successful testing and successful combat were entirely different things. The first LST saw actual combat in November 1942 during Operation Torch, the Allied invasion of North Africa. 3 LSTs participated, landing tanks and troops at Oran. The ships performed adequately, but the operation revealed problems the test beach at Quonset Point hadn't simulated. Enemy artillery fire was terrifying for crews in vessels with thin steel hulls. The LST's armour was designed to keep water out, not shells. A direct hit from even a medium-caliber gun would penetrate easily. Crews nicknamed their ships large, slow targets, not as affection but as gallows humour. They were slow targets, and they were large targets, and they operated in the most dangerous environment imaginable, the transition zone between sea and land, where naval gunfire couldn't suppress shore batteries, and the landing force hadn't secured the beach yet. The Sicily invasion in July 1943 provided the first large-scale test. Operation Husky threw 160,000 Allied troops at Sicily's southern coast. Logistics immediately became the choke point. Conventional landing craft delivered troops to shore successfully, but supplies piled up in chaotic mountains along the waterline. Artillery shells stacked beside medical supplies. Ammunition crates sat exposed under the Mediterranean sun, while German reconnaissance planes circled overhead. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. LSTs changed that calculus dramatically. They drove straight from transport positions offshore, beached themselves, opened their massive bow doors, and began disgorging cargo directly onto the sand. Tanks rolled down the ramps under their own power. Trucks drove straight from the tank deck to inland positions. Artillery pieces could be towed immediately to firing positions, rather than being manhandled from landing craft to shore to trucks. The efficiency gain was measurable. A conventional supply chain required landing craft to beach, soldiers to manually unload supplies onto sand, separate trucks to collect those supplies, and a minimum of 45 minutes per cycle. An LST could beach in minutes, unload through its bow doors in 20 to 30 minutes depending on cargo configuration, then retract using the stern anchor winch and return to the transport anchorage for another load. More importantly, the LST eliminated the vulnerable beach stockpile. Supplies that sat exposed on sand for hours while waiting for trucks became targets for German artillery. LSTs delivered cargo directly to collection points inland, often under cover or defied, where enemy guns couldn't easily range them. General George Patton, commanding the 7th Army in Sicily, saw the potential immediately. He sent urgent requests to Allied headquarters, demanding every available LST be assigned to his sector. The response couldn't meet his demands because there simply weren't enough LSTs yet. Dravo and the other inland yards were still ramping up production. The ships completed in late 1942 and early 1943 were only just reaching operational theatres. By September 1943, the Italian mainland invasion began at Salerno. This operation demonstrated both the LST's capabilities and its vulnerabilities. German forces had prepared extensive beach defences. Artillery positions covered the likely landing zones. The flat trajectory guns could hit LSTs while they were still offshore, before they could beach and unload. Several LSTs took direct hits. The thin hulls offered virtually no protection. LST-312 was struck by an armour-piercing round that penetrated the hull below the waterline. Water flooded into spaces that weren't designed with watertight subdivisions. The crew fought to control the flooding while still completing their unloading mission. They succeeded, barely, and managed to retract from the beach before the flooding became catastrophic. The lesson was clear. LSTs couldn't survive prolonged exposure to artillery fire. They needed to get in, unload, and get out as quickly as possible. The longer they sat beached, the more vulnerable they became. This drove training modifications and operational procedures. Crews drilled relentlessly on rapid unloading, choreographed sequences for offloading tanks, trucks, and supplies in minimum time, pre-positioned cargo, practiced stern anchor operations until the winch crews could retract the ship in under 10 minutes after the last vehicle rolled off the ramp. The Pacific theatre presented entirely different challenges. European beaches were sand and shingle, relatively predictable surfaces. Pacific islands featured coral reefs, volcanic rock, and steep gradients that made beaching operations treacherous. The LST's flat bottom could scrape over coral that would tear the hull out of smaller landing craft, but repeated impacts with sharp coral edges caused cumulative damage. Pacific operations also revealed the stern anchor system's limitations. In calm water with good holding ground, the anchor worked beautifully. In surge conditions with coral bottoms, the anchor would skip and drag, failing to provide the pull needed to retract the ship. Crews learned to read bottom conditions and adjust anchor deployment. In some cases, they'd use kedge anchors, smaller secondary anchors positioned at angles to provide lateral stability, while the main stern anchor pulled the ship backward. But the real test, the operation that would either justify the entire LST program or expose it as inadequate, was still coming. D-Day, the invasion of Normandy, June 6, 1944. The largest amphibious operation in human history would require more LSTs than had ever been assembled for a single operation. Allied planners designated 173 LSTs for the Normandy invasion force. These ships would carry the armoured punch that would break through German beach defences and establish a lodgment strong enough to sustain the liberation of Europe. The English Channel in early June was cold, grey, and unpredictable. Weather forecasting in 1944 was primitive by modern standards. General Eisenhower had to make the invasion decision based on meteorologists' best estimates that there would be a brief window of acceptable weather, starting June 6. Even during that window, conditions would be marginal. Rough seas, low clouds, crosswinds. LST crews loaded their vessels at ports across southern England during the first days of June. The loading process had been refined through 2 years of experience. Tanks positioned first, toward the bow, their weight providing stability, trucks behind them, artillery pieces secured to deck points, ammunition stored in designated spaces below deck, gasoline in jerry cans stacked and secured, everything lashed down because the channel crossing would be rough. Each LST carried approximately 100 troops in addition to its naval crew of around 120 men. These soldiers and marines bunked in temporary spaces rigged throughout the ship. Hammocks hung in passageways. Men slept on deck when weather permitted. The accommodations were miserable, but the voyage was short. 12 hours from English ports to the Normandy coast. On the night of June 5th, the invasion fleet departed. Hundreds of ships of every size and type organized into convoys by destination beach. LSTs sailed in formation, their flat bottoms making them roll sickeningly in the swells. Men who'd never experienced seasickness before now hung over rails, vomiting into the dark water. Below decks, the air was thick with diesel fumes, sweat, and fear. The night crossing was chaotic and terrifying. Ships maintained radio silence to avoid alerting German defences. Navigation lights were blacked out. LSTs wallowed through the darkness, trying to maintain position in convoy while waves rolled them 40 degrees to each side. Collisions were avoided by luck and the skill of officers who'd learned to operate these ungainly vessels through months of training. Dawn came grey and cold. Through the mist, the French coast materialized. From several miles offshore, LST crews could see the beaches: Omaha, Utah, Gold, Juneau, Sword. Each designated landing zone was marked by naval vessels already pounding German positions with naval gunfire. Smoke from explosions drifted across the water. The sound of artillery was continuous thunder. The assault waves had already gone in, small landing craft carrying infantry to establish the initial beachhead. The LSTs were scheduled for later waves, after the beaches were theoretically secured. Theoretically, at Omaha Beach, nothing was secure. German resistance was far stronger than intelligence had predicted. The initial assault waves were pinned down, taking catastrophic casualties. The beach was a killing zone. LSTs approaching Omaha could see the carnage even from their offshore positions: wrecked landing craft at the waterline, bodies floating in the surf, soldiers huddled behind beach obstacles under withering machine gun fire. Several LSTs that tried to approach took direct hits from German artillery that had survived the naval bombardment. LST 521 was struck above the waterline. The shell penetrated the hull and exploded in a cargo space, killing 3 crew members and wounding a dozen more. The ship's commanding officer faced an impossible choice: withdraw and fail to deliver the tanks desperately needed on the beach, or continue the approach and risk being hit again, potentially losing the ship and everyone aboard. He continued. LST 521 drove through the impact zone, took another hit that fortunately failed to penetrate critical spaces, and beached successfully. Her bow doors opened and tanks rolled directly into the fight. At Utah Beach, the situation was dramatically different. The assault waves had landed in the wrong location due to strong currents, but that accident proved fortunate. The alternate landing zone had lighter defenses. By mid-morning, Utah was relatively secure. LSTs could approach with less risk of artillery fire. The scene at Utah became a demonstration of the LST's design intent. Ships formed a rotation pattern: 20 LSTs at anchor offshore, loading from transports, 20 approaching the beach, 20 beached and unloading, 20 retracting and returning to the anchor position. A continuous cycle, like a conveyor belt of steel carrying war materials from ship to shore. Bow doors open, ramp down. Unload everything, 20 to 40 minutes depending on cargo. Engage the stern winch, retract from the beach, 10 to 15 minutes. Return to the transport position. Reload. Repeat. The numbers were staggering. In the first 48 hours after D-Day, LSTs moved over 130,000 troops and 17,000 vehicles across the beaches. By the end of the first week, that number exceeded 400,000 troops and 60,000 vehicles. The beaches became organized chaos, but organized chaos flowed because LSTs could deliver cargo directly to collection points rather than creating bottlenecks at the waterline. The British beaches, Gold, Juneau, and Sword, employed similar LST operations. The Royal Navy operated LSTs built in British yards to slightly different specifications, but the concept was identical. Beach the ship, unload, retract, repeat. The efficiency was unprecedented in amphibious warfare. Then, on June 19th, a massive storm struck the English Channel. Winds exceeded 50 miles per hour, waves built to 8 feet and higher. The storm destroyed the American Mulberry Harbor at Omaha Beach, the artificial port that was supposed to handle the deep draft supply ships. Conventional landing operations ground to a halt. Small craft couldn't operate. The invasion's logistics threatened to collapse just as Allied forces were pushing inland and needed maximum supply flow. LSTs saved the operation. Their flat bottoms and high bows handled the rough conditions better than the open landing craft. When 8-foot waves were swamping Higgins boats, LSTs could still make beach approaches. The ships would time their approach to ride wave sets, diving through faces rather than trying to climb over peaks. It was dangerous, and several LSTs broached in the surf, turning sideways and nearly capsizing before crews regained control. But they kept operating when nothing else could. General Eisenhower's after-action report specifically credited LSTs with preventing a logistics collapse during the storm. Without them, he wrote, the invasion timetable would have been set back by weeks. Troops already ashore would have run critically low on ammunition and supplies. The entire Normandy lodgment could have become untenable. Crews learned to play the anchor cable like a fishing line, letting out slack when waves pushed the bow sideways, then reeling in to pull the stern back into alignment. Some crews became artists at stern anchor operations. They could beach their LST, unload in rough surf, then retract cleanly even when waves were breaking over the bow. Others struggled and required assistance from harbour tugs. The difference was usually experience and nerve. Working the anchor winch while waves crashed over the ship required ignoring the terror of being on a grounded vessel in storm conditions and focusing on the Bren, mechanical task. By the end of June 1944, Normandy operations had validated every design decision Niedermair made in that 1st November 1941 sketch. The ballast system allowed ocean crossing and beach operations. The bow doors and ramp enabled rapid unloading. The stern anchor provided retraction capability even in rough conditions. The flat bottom absorbed the repeated impacts of beaching without structural failure. But the Pacific theater was simultaneously demonstrating that LSTs could exceed even their design parameters. In the island-hopping campaign across the Central Pacific, LSTs became the primary logistics vehicle for operations that occurred thousands of miles from major ports. The invasion of Saipan in June 1944, happening simultaneously with Normandy, involved LSTs operating under conditions the designers never anticipated. Saipan was surrounded by coral reefs extending hundreds of yards offshore. These reefs were under several feet of water at high tide, invisible to approaching ships. At low tide, they became exposed barriers that conventional landing craft couldn't cross. LSTs drove over the reefs. Their flat bottoms would scrape across coral heads, grinding and bouncing, hull plates flexing under the impacts. Crews below decks could hear the coral rasping against the steel, a sound like tearing metal that suggested the hull was being ripped open. But LST hulls were built from thick steel plate, reinforced at the bottom. The coral scarred and dented the plating but rarely penetrated. Once past the reef, LSTs would continue into the lagoons beyond and beach on the actual shoreline. Japanese defenders quickly learned to target the ungainly ships. Artillery and anti-tank guns would engage LSTs as they approached. The thin hull armour meant that direct hits often penetrated. Several LSTs were sunk by Japanese fire at Saipan. LST 341 took a direct hit from a 75mm gun while beached and unloading. The shell penetrated the starboard side and exploded in the tank deck. Burning gasoline from ruptured fuel drums spread across the deck. The crew fought the fire while simultaneously continuing to unload tanks because the Marines ashore desperately needed the armour. The ship completed its mission, retracted under fire, and made it offshore before the structural damage became critical. The Pacific War also revealed the LST's versatility beyond simple cargo delivery. Ships were converted into repair vessels, fitted with machine shops and welding equipment to repair damaged tanks and vehicles in forward areas. Others became hospital ships, their tank decks converted to hold hundreds of wounded. Some carried pontoon causeway sections on their main decks, essentially serving as mobile bridge components. The Battle of Leyte Gulf in October 1944 involved over 300 LSTs supporting the invasion of the Philippines. This operation demonstrated the full maturity of LST operations. Ships were organized into groups by cargo type. One group carried fuel, another carried ammunition, a third carried rations and supplies. This specialization allowed beachmasters to call forward specific LSTs as needed, rather than having mixed cargo that required time-consuming sorting. The coordination was extraordinary. LSTs would receive orders by radio to beach at specific locations at specific times. They would approach their designated beach, drop anchor at the planned point, beach on schedule, unload their specified cargo, then retract and return to the transport anchorage. The entire cycle was choreographed like a ballet performed by 300-foot steel dancers. One innovation that emerged in the Pacific was the use of pontoon causeways deployed directly from LST main decks. Engineers designed these floating roadways in sections that could be carried on an LST's upper deck. When approaching a beach with a steep drop-off that prevented the LST from getting close enough to drop its bow ramp onto dry sand, the ship would stop offshore and deploy the causeway sections. The pontoons would be rolled off the deck, assembled in the water to form a floating bridge, then anchored with one end attached to the LST's bow ramp and the other end extending to the beach. Vehicles could then drive off the LST, across the pontoon causeway, and onto dry land without ever getting wet. The system extended the LST's effective reach and allowed operations on beaches that otherwise would have been unusable. By early 1945, LST operations had become so refined that beach unloading times averaged 23 minutes for a full load of vehicles and cargo. Some highly trained crews could complete unloading in under 20 minutes. This efficiency meant each LST could make more trips per day, effectively multiplying the logistics capacity of the entire amphibious fleet. The invasion of Okinawa in April 1945 represented the peak of LST operational art. Over 340 LSTs supported the operation, the largest number ever assembled for a single invasion. The ships operated under the constant threat of kamikaze attack. Japanese suicide pilots specifically targeted the LSTs, recognizing them as critical logistics nodes. LST gunners shot down dozens of kamikazes during the Okinawa campaign. The ship's anti-aircraft armament had been continuously upgraded through the war. Early LSTs had a few 20mm guns. By Okinawa, they bristled with 40mm quad mounts and additional 20s. The volume of fire a formation of LSTs could put up was formidable, but kamikazes still got through. LST-447 was hit by a Zero that crashed into the bridge structure. The resulting fire killed 17 crew members and wounded 30 more. The ship survived and continued operating after emergency repairs. LST-808 wasn't as fortunate. A kamikaze penetrated the anti-aircraft screen and crashed directly into the open tank deck while the ship was beached and unloading. The explosion of the aircraft combined with secondary explosions from ammunition and fuel aboard the LST. The ship was a total loss. These losses were tragic but statistically minor. Of the over 1,000 LSTs that operated during World War II, only 26 were lost to enemy action. The survival rate exceeded 97%, despite operating in the most dangerous possible environment, the transition zone between sea and land, where they were vulnerable to both naval threats and land-based artillery. Part of that survival rate came from the ship's inherent toughness. The flat-bottom hull and internal structure could absorb tremendous damage and remain operational. Multiple redundant systems meant that battle damage to one area didn't necessarily disable the entire ship. And the shallow draft meant that LSTs sat high in the water with relatively little hull below the waterline, reducing the target area for torpedoes and mines. But part of the survival rate also came from the crew's skill and courage. Operating an LST required a unique combination of seamanship and ground operations awareness. Commanding officers had to understand tides, beach gradients, surf conditions, and enemy defences. They had to coordinate with beachmasters ashore, naval control vessels offshore, and their own crew managing the complex ballast, anchoring, and unloading procedures. The enlisted crews developed their own expertise. Beachmaster teams could assess a beach's suitability for LST operations by reading the wave patterns and calculating the gradient. Stern anchor crews could drop the hook at exactly the right moment to pay out the correct amount of cable. Winch operators learned to feel through the controls when the ship was breaking free from the sand versus when they were straining against too much suction and needed to use engines to assist the retraction. By the time Japan surrendered in August 1945, LSTs had participated in every major amphibious operation in both the European and Pacific theatres. They'd delivered millions of tons of cargo, hundreds of thousands of troops, and tens of thousands of vehicles directly onto hostile shores. The ships had proven so successful that post-war planning assumed any future amphibious operation would require LSTs as the primary logistics vehicle. The wartime production figures were staggering. 1,051 LSTs were built in American shipyards during the war. 670 came from the 5 inland cornfield shipyards, with the remainder built in coastal facilities that had been freed up as other wartime construction programs completed. Dravo alone built 145 LSTs. Missouri Valley Bridge and Iron in Evansville built 171, the most of any single yard. Construction time declined dramatically as the yards gained experience. In 1943, building an LST took approximately 4 months from keel laying to commissioning. By 1945, that time had been cut to 2 months. The prefabrication systems perfected, the welding procedures proven, the workforce trained to high efficiency. Those 1,000-plus LSTs represented not just ships, but a complete rethinking of amphibious warfare logistics. Before the LST, invasions were constrained by port availability. Armies had to capture deep-water ports early in any campaign because that was the only way to sustain logistics for large forces. This meant defenders could predict where invasions would occur and concentrate defenses accordingly. LSTs eliminated that constraint. Any beach with a gentle slope became a potential invasion point. This strategic flexibility forced defenders to spread their forces across hundreds of miles of coastline rather than concentrating at ports. The uncertainty about where the blow would fall, the strategic flexibility that LSTs provided became their most profound legacy. By making every beach a potential landing zone, they fundamentally altered defensive calculations and enabled offensive operations that would have been impossible with port-dependent logistics. When the war ended in August 1945, the Navy found itself with over 1,000 LSTs scattered across the globe and no immediate need for them. Initial plans called for scrapping the majority. The vessels were wartime emergency construction, not meant for long peacetime service. Their crews were eager to return home. The ships themselves seemed destined for the breakers' yards. But the LST proved too useful to discard. Roughly half were eventually scrapped. 20% were converted for commercial use, their tank decks becoming cargo holds for civilian shipping companies. 18% were sold to foreign governments under military assistance programs. Nations building their own amphibious capabilities recognized that the LST concept was sound regardless of whether a war was happening. The Korean War in 1950 vindicated the decision to maintain an LST fleet. The Incheon landing in September 1950 employed LSTs that had sat in reserve since World War II. Their crews were new, but the ships performed exactly as designed. Once again, they delivered tanks and supplies directly onto hostile beaches, enabling an amphibious operation that changed the course of the war. Vietnam saw LSTs operating in riverine environments their designers never imagined. The Mekong Delta's shallow waterways were perfect for the flat-bottomed ships. They could navigate rivers that were too shallow for conventional cargo vessels, delivering supplies directly to remote outposts. The Navy built improved LST classes in the 1950s and 60s, incorporating lessons from 15 years of operational experience. The last LST in U.S. Navy service, USS Frederick, was decommissioned in October 2002, 60 years after LST-1 was commissioned. Some foreign navies still operate modernized versions today. The basic concept, a ship that can cross oceans and beach itself to unload cargo, remains valid because the underlying logistics problem hasn't changed. But the LST's real legacy isn't the ships themselves. It's the validation of an approach to engineering problems that prioritized practical functionality over conventional wisdom. When Niedermair sketched his ballast system design, he wasn't following established shipbuilding doctrine. He was solving a specific problem with whatever tools worked, regardless of whether they fit traditional naval architecture. The inland shipyards demonstrated that complex engineering projects could be executed by people who'd never done that specific work before, if the training was adequate and the motivation was high. The women welders at Dravo and American Bridge proved that gender barriers in heavy industry were artificial constraints, not natural limitations. When the need was urgent enough, society discovered that capabilities existed in populations it had previously excluded. The prefabrication and modular construction techniques developed for LST production influenced post-war shipbuilding globally. The idea of building large sections in controlled environments, then assembling them rapidly on the ways, became standard practice. Modern shipyards still use variations of the processes Dravo pioneered in 1942. The stern anchor system, seemingly simple in concept, represented sophisticated engineering applied to a unique problem. That willingness to create custom solutions rather than adapting existing technologies became a hallmark of American wartime innovation. If the problem was unprecedented, the solution could be unprecedented too. John Niedermair continued working for the Bureau of Ships throughout the war and afterward, designing other vessels and advising on naval architecture problems. He never achieved the public recognition of weapons designers or combat commanders. His contribution was enabling logistics, the unglamorous background work that made dramatic operations possible. The LST succeeded because it was designed for a specific mission and optimized relentlessly for that mission alone. It wasn't the fastest ship, it wasn't the most heavily armed. It couldn't win battles through firepower or speed, but it could deliver the tools that won battles to the places they were needed, and do so reliably under conditions that stopped every other method. That morning in February 1943 at Quonset Point, when LST-1 drove onto the beach under Niedermair's direction, validated more than a ship design. It validated the principle that impossible requirements could be met with creative engineering and the courage to test concepts that contradicted established practice. The young lieutenant who hesitated to run his ship aground learned something that every LST commander afterward internalized. Sometimes the rules that exist to prevent disasters in normal circumstances have to be violated deliberately to accomplish extraordinary missions. The LST was designed to be grounded. The articles of government said ships shouldn't founder on rocks and shoals, but LSTs did it successfully thousands of times because that was precisely what they were built to do. The legacy lives on every time engineers face contradictory requirements and refuse to accept that the problem is unsolvable. Every time production experts implement modular construction to achieve impossible timelines, every time military planners design operations around logistics capabilities rather than assuming logistics will somehow support whatever strategy they devise. John Niedermair received the Distinguished Civilian Service Award for his contribution to the war effort, though his name never achieved the recognition of military commanders whose strategies his ships made possible. He continued serving at the Bureau of Ships until his retirement, designing vessels that would influence naval architecture for decades to come. His willingness to challenge conventional wisdom and solve seemingly impossible problems became his lasting legacy in the field. The LST design principles continue to influence modern military and civilian vessels today. From the U.S. Navy's current landing craft air cushion, LCAC, to commercial roll-on roll-off ferries, Niedermair's innovative approach to the sea-land interface remains evident. His creation proved that sometimes the most unglamorous solutions, like a flat-bottomed ship nicknamed a large, slow target, can have the most profound impact on history. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.